Hello, everybody. What I'd like to talk about today is the perspective from a consultant's point of view about recent innovations in pipeline integrity and the future of pipeline integrity, particularly with reference to digitalization. And I'd like to add, this is our perspective. You know, operators would have a different perspective. Technology providers would have a different perspective. So Penspen have been in the business for about 25 years. So this is the combination of that knowledge. So this is what I'd like to cover today. First of all, just to make sure everybody's on the same understanding about pipeline integrity and how it's part of enterprise risk management. Talk about what we're calling the industry quadrilemma. Typical scenario with regard to pipeline integrity management as it typically is now. Developing background in technology and expectations, what's called the fourth industrial revolution or industry 4.0, or what we'd like to call pipeline 4.0. A little bit about new data sources and new data sources. Some examples of our current developments and research, and where we think that the challenges and roadblocks are to what we are trying to do and other parts of the industry are trying to do. So firstly, most operators, if not all operators, have some kind of perspective of enterprise risk management. There's a standard for this, and this would include the broad existential risks, for example, commodity risk, oil price fluctuations, existential risks such as pandemics or strikes, etc. But part of that is the risk associated with the asset or the pipeline asset in this case. So really, pipeline integrity management is managing the risk that the asset poses to the environment, people, reputation, and the business. And you'll find that these are all wrapped up into aims, but you'll find FIMS, Facilities Integrity Management System, Structural Integrity Management Systems, and even well integrity management systems. The concept is the same. It's really risk management through the life as part of enterprise risk management and most of these are owned by operators, of course. So one important observation that we've made over the last few years is what we're calling the quadrilemma. So it's 4 challenges facing the industry. The first one is obviously the core to integrity management, which is aging assets. You may be familiar with the bathtub curve, which is a bathtub shape where you find in early asset development you get infertile failures, and then you have a long period of a reduced number of failures, and at the end you get the wear out phase. Now pipelines tend to exhibit this behavior, and in the UK alone, there are pipelines that were built in the 40s, 50s, and certainly 60s and 70s, and in the US we may even see a 100-year-old pipeline coming along. So there are lots of pipelines, with developing issues. And one aspect of this, of course, is that the pipelines that were built in the 60s, 40s, 50s, and 60s weren't built to the same standards that we currently apply. So the second point is scarcity of resources, and I'm not talking about steel or oil there. This is really people. There's been the up and down of the oil price. I think retirees and movement of staff, and also I think fundamentally the ability of the industry to attract young engineers has led, unfortunately, to a scarcity of resources. You see this, we run a global business, and you see this pretty much everywhere. There is a shortage of people trying to recruit an experienced integrity engineer. They take a long time to grow. They need a science-based degree and then probably 10 years of experience. And the third one is legislation. Increasing legislation. Governments are aware of the risk that pipeline assets or assets generally pose to their income, taxable revenue, and also to the environment and people. So you may be aware in the UK there's a new legislation which is maximizing the economic recovery of oil. And this gives the oil and gas agency powers to remove licenses, to issue penalties to operators that can't demonstrate that they're maximizing the recoverable resources in the UK. Now, this is clearly a good thing, but you know, it's another burden for operators that they have to worry about. And also, new financial outlook, significant fluctuations in oil price, commodity prices, or even negative oil prices lead to uncertainty, lead to less money available to do things. And if you are charging a tariff for transportation, then less transportation revenue as well. So really, these four things work together to make life tough for operators, and obviously we're supporting that process as a consultant. So now the broad topic of pipeline integrity management, there are lots of advice codes and standards. They've all been written in the last 15 or 20 years. You know, some US based, some European based, some Norwegian. And we came up with our own. We call them the 17 elements, which is a broad, holistic way of looking at pipeline integrity management. Because you're probably aware, to manage it properly, you need to cover a wide variety of different aspects of an organization, including quality assurance, health, safety and environment, human resources, legal, projects, maintenance and procurement. So it's to be done properly. It's a holistic process. And another way of looking at it really is, again, back to risk management, is really managing the risk throughout the life of the asset. This is projected risk, because obviously during the design phase, the actual asset isn't producing a risk to the environment or people, but projecting it forward. So during the design phase, you optimize your design and produce control measures, which could be based on routing for a high pressure gas line. It could be based on wall thickness and the glass location. And eventually you need to demonstrate typically that it's as low as reasonably practical, and no further measures are required on a as low as reasonably practical basis. Then you can move into the construction phase. Now the risk produced by the construction phase will almost certainly be different from that predicted during design, but whether it's more or less, here we've assumed it to be the same. And then finally you go into operation, and this is where the bathtub comes into play. As you get towards the end of the life of the asset, you have the wear out phase, and you start to get issues such as coating degradation, fatigue damage, external corrosion, internal corrosion, or system decay. And then due to making decisions or inspection, you might choose to actually do something. That could be you repair your pipeline, you introduce inhibition, or you reduce the operating pressure. There are a number of different scenarios, and you go through managing the risk through the pipeline's life, and then eventually you reach the point where the risk is unacceptable. I'd say you reach the point where the risk is unacceptable, or the asset is not providing a positive net present value. In other words, doesn't satisfy a business function anymore. And then you can decommission it, and then the risk reduces to almost nothing. Not absolutely nothing, because depending on where the pipeline is, you'll still have some ongoing obligation. You know, the concept of abandonment is a complicated one, because you'll still have potentially, you know, an abandoned or a pipeline which is not operated still potentially can produce risk to the environment or to people. So, you know, in our experience of looking at the way operators manage this process, it's very patchy. Typically, we've not really come across many operators that have you know, a full enterprise solution to this. Most operators, large and small, have a proliferation of spreadsheets, multiple legacy ERP systems, and particularly bearing in mind that the acquisitions and mergers that have gone on in the past, you'll find that there'll be all sorts of enterprise systems that'll be used. Multiple, highly disparate data sources, some paper, some in spreadsheets, some in databases, some in documents, and unfortunately, we've often come across situations where it's been lost as well, so gone. Often single user applications, thick client, doing a very, very specific thing, but no real connectivity with other applications. So with this, I would say that, and also with the limited resources, quite often it's difficult for operators, in our experience, to achieve the minimum. And when you start to think about some of the requirements for generating KPIs or producing KPIs, you need to collect information from the whole organization. It becomes very, very unwieldy. And there really is, I think, in a lot of cases, a loss of the ability to make, good insights. A lot of effort going into turning the handle, and not much into getting a big picture or an oversight. So now, I used to be very skeptical about enterprise solutions to this. I think certainly in the 90s, there were a lot of attempts, with large and small operators to integrate all of this together. In our experience, not many of those have been very successful. It's a difficult thing to do with the situation that currently exists. However, things are quite dramatically changing, certainly in the last 10 years, 5 years, or even the last couple of years. So with a background of involving technology, artificial intelligence on the rise, and there are considerable advances in computer power. There's been a 10,000-fold increase in processing power since 2000. There's a 3,000-fold in reduction in storage since 2000, and almost typically across most industries, an exponential growth in data. And you see the chart on the right. The computing power has actually slowed down since about 2010, but in terms of pure computing power, and particularly in the context of artificial intelligence, GPU or graphics processor unit computing has kind of taken over for the very computational expensive things. A typical Intel i9 top of the range has 10 cores and 20 threads, but CPUs, or GPUs rather, have a slower clock speed, and they have a smaller instruction set, but there are thousands of them. The NVIDIA GeForce RTX 2080 has 4,352 CUDA cores, and you can get 5,000 plus available in virtual GPUs as well. So really, the GPU is for computational expensive calculations has really taken over from the CPU, and again, available virtually. The other very important development is just cloud-based computing generally. In terms of web services, there's a whole wealth of web services being developed to do all sorts of apply all sorts of different technologies. For example, optical character recognition that can be used for taking payments, getting data, performing analysis, storing data, and much of it's free, and a lot of it's very, very low cost. And also open source applications as well. MongoDB, a non-SQL database, Postgres SQL. Kubernetes allows you to put a variety of different languages, into an online cloud environment and do calculations from a server basis. Jupyter notebooks for sharing computer code. Angular for graphical user interfaces. Elasticsearch for very, very powerful searching. And these have thousands of users, and thousands of developers always being developed. So really, that there's a incredible technology being developed and available generally. And I think expectations as well. Generally, most of us at home are used to getting everything a few clicks away. You know, using Amazon and Google, we can get pretty much anything we like, and really, there's no real reason why some of this technology couldn't be applied to the pipeline integrity industry. You know, and I don't think there's really any way back from this. I think this is clearly here to stay. So you may or may not have heard the term the fourth industrial revolution, and this makes reference to the progression from steam power, industry 1.0, electric power, industry 2.0, automation, you know, maybe starting about 20 years ago, and then now we're into hyper connectivity. So this is industrial Internet of Things, IoT, you know, artificial intelligence, machine learning, big data, and live data. So this is computers, you know, making good decisions and developing insights without interaction from humans effectively. So, and also there is a proliferation of low cost sensors. You know, that are obviously aimed at taking advantage of this technology. This can give live or quasi-live real-time data, and includes sources such as pipeline strain gauges. Of course, a lot of this technology has been around for some time, but not in such an affordable and obviously with advantages of communication as well. Pressure monitoring, temperature monitoring, vibration monitoring, process monitoring, cathodic protection monitoring, you know, satellite, LiDAR, field verifications, weather forecasting again is available for free from web services. You know, again, seismic monitoring, you know, again from web services. Also collecting one call data as well. It's where people are calling, you know, one number to report activities close to a pipeline. So, and also new data sources as well. We're getting increasingly better satellite data with low orbit satellites. There are new technologies with synthetic aperture radar, which can be used for getting sub-millimeter measurements of ground displacements. These are being used extensively in cities that have poor ground conditions for monitoring displacements of buildings for risk assessment. I'm not sure where it's been applied to pipelines yet. LiDAR certainly has been applied to pipelines, but that's harder to collect, normally requiring a plane or an autonomous vehicle to collect LiDAR data. But potentially this could be done, you know, over the net, effectively collecting data from a third party. So what does Industry 4 have to benefit the pipeline business? Now, some things, in some places we are there already. You're probably aware there are fiber optic systems that can give very, very good determinations of things like strain, temperature measurements, which can be used for leak detection. They can be used for right-of-way monitoring. You know, they can detect digging or vibration that could be used to prevent theft, ground movement. But it's possible, you know, that not many of these integrated, but they can be included depending on the threat for live fitness of purpose assessments. For example, some of our clients have pipelines where the main threat is from land movement. So you can actually install ground movement sensors or fiber optic cables, so you can actually get a real-time measurement of strain and actually relate that to a failure criteria to get a live fitness for purpose. You know, incorporating all this into live dashboards. It's possible to have live validation of inspection periods, predictive analytics for live risk management, you know, and preemptive maintenance planning. Also, dynamic lifecycle costing is already a technology used in other industries for jet engines and mining equipment, where you have a forward prediction of your lifecycle cost that helps you make decisions about maintenance or obsolescence on repairs. You know, no reason why we couldn't apply the same technology to pipelines. I'm going to talk a little bit about some of the experiments we've been doing with some of this methodology. Now, for doing integrity assessments, matching subsequent inspection data is a very critical process. Excuse me. You need to do this to allow you to predict prediction corrosion rates or rates of degradation. And this all really relates around the girth weld number, because to make a judgment about a pipeline, you've really got to relate it to girth welds, because KPs or kilometer points tend to drift along the length of the pipeline. So we've tried a number of different techniques, fast Fourier transforms. We've used annealing and relaxation methods, and they both work very, very well, very, very quick. They take fractions of seconds, and we compare it with our manual methodology we've used in the past, and it spots things that you wouldn't normally spot. So much better. So really, the benefit of this is much better predictions. Also, we've been experimenting with variable corrosion rates. From a long pipeline, typically internal corrosion and remaining life is based on a single corrosion rate. But in practice, there could be, for a long line, lots of things going along. Drains, cathodic protection systems, third-party interactions, damaging coatings, changes in corrosion mechanisms, natural causes, lightning strikes, etc. So again, we've been using this technology to actually to develop corrosion rates along a pipeline to provide a better diagnosis and a better understanding of mechanisms, allowing better failure predictions, and of course, better decisions, which is really the important thing in the end. So the other area of exploration for us has been massive parallel computing, using virtual GPUs or actual GPUs. This is a failure surface of ASME modified B31G, and we've actually to do this in a conventional. There's the first order reliability method or the second order reliability method. They have some computational disadvantages or impracticalities, but a very robust way of dealing with this is using Monte Carlo simulation. But this is very, very computational and expensive, and you can get runs that go into years. So if you're trying to produce a complete failure surface, it can take a long time. But using GPU parallelization, we managed to make this much faster. In fact, runs that could potentially take days or months or even years, we've got down to seconds. Also, we've been optimizing this using subset simulation, which focuses on the low probabilities of failure. And also, we've been using artificial intelligence or machine learning to actually fill in the gaps. So we populate the failure surface with a number of points and then fill in the gap. So really the benefit here is that we can shift to probabilistic remaining life calculations, probabilistic assessments, which give benefits, rather than a deterministic perspective, i.e. your pipeline will fail after 20 years. You can say that your pipeline has a probability of failing of this by 20 years, and the probability of this will be 30 years. So, it allows you to make better informed decisions. Also, applying the same technology to very complex corrosion features as well. This is a 12-meter long corrosion feature which we experimented with, and using the PRC R-string methodology with a 1.5 millimeter spacing, that gives us about. The methodology actually includes a combination of the various parts of the defect. This will give us 32 million combinations. So to do a probabilistic calculation on 32 million different combinations would take almost an infinite amount of time. In fact, we worked it out. It sounds like ridiculous, but we worked it out to be about 100,000 years using that methodology. But we've managed to get it down to tens of minutes by combining all these different enhancement techniques. Another thing we've invested a lot of time and effort into is really doing assessments. That's a core business for us. And this is where you can take multiple sets of inline inspection data, multiple construction data, operations and historic data, and produce an assessment literally in 30 seconds. So you ingest the data, go right the way through, and obviously the benefits of this that it's highly accessible, very, very fast, an insight, and you can apply insights as well. The other thing that we are contemplating and working on is dynamic lifecycle costing. This is currently a very long drawn out process, collecting pressure data, which can be thousands of points, calculating equivalent life cycles, fatigue analysis, manually aligning ILI data, estimating costs of failures, estimating whole life incomes for whole life costs, calculating MPVs, for economics. It's very, very long, very long and drawn out, taking months potentially. But really, we're pretty confident we can automate this process. So really, our vision, getting back to the enterprise solution for pipelines is really to develop a native cloud-based solution, not virtual machines or remote desktops, but native cloud, and integrate with existing ERP solutions, which are for sure here to stay with most operators. And that's including solutions like Maximo, Esri, and SAP, to automate data ingestion and alignment using smart recognition. So you can pretty much take any kind of data format, and includes things like data document management, live data feeds, flexible user-defined holistic KPIs, role-based portals for collecting KPI data, e-learning solutions, so you can use it to train up people, document libraries, and benchmarking. So we've completed some of this, but this is kind of our vision for a cloud-based enterprise solution. In terms of challenges, it's a key question really. I mean, this type of technology can be very accessible, but do really operators want to take responsibility for it and do that by themselves? That's not clear. But certainly aspects of it they will, and it's certainly an efficiency for us as a consultant. Also, investing in legacy systems. A lot of people, including us, have got investment in legacy systems which don't conform well to this type of thinking. Sensorization, I think I invented a new word there, but obviously it's expensive. Would you apply that to old pipelines? And lack of interoperability between IT systems. So I'm actually running a bit short on time, so I'm gonna speed up a little bit. So another thing we found is a change in skill requirements. We're automating now our assessments and some of our work. So really, people have time to spend more on insights and taking a high-level view. So really, data science, programming are becoming more important skills for us, than someone that's capable of doing an assessment, which is kind of changing the dynamics of our industry, of our organization, and also it's affecting our ability to hire people as well. It's offering a different kind of role. Security is a concern for a lot of operators in the Middle East. There's quite a high resistance to cloud-based solutions. Some operators have ruled it out completely. General concerns over unauthorized access. But we've got ISO 27001. That has a very, very important checklist. And you can use multi-factor authentication. You can use hierarchical hackers, and we've applied this methodology to our environment. I have got time to go through this, but this is effectively what we're using. It's a combination of open source technology to provide a whole range of functionality based on file-based data, using APIs to gather data for other enterprise systems or real-time devices, and produce procedurized processes to produce cogent output across a whole range of different things. So in summary, digital transformation using cloud computing, open source, web services, and Industry 4 concepts has a lot to offer the industry. Once implemented, we think it will give easy access to resources, better insights, and make better decisions. There are roadblocks, but we can see that some of those will be overcome. The industry could benefit, I think, for a closer cooperation in some areas, particularly data transfer protocols. I think the acceptance of cloud computing will come eventually. And I think the other thing is hiring engineers that understand data science, understand coding, can do coding. From our experience, trying to explain pipeline integrity concepts to computer programmers can be a bit of a challenge. We've been facing that almost on a day-to-day basis. No disrespect to computer programmers. So finally, I think that's it from me, and I believe Annie is going to facilitate some question and answering session for us.